So this is SLT, Single Learning Theory seminar session, the main session 2. Today, it will be mainly about the following things that you see in the first board there. So my goal is to motivate and introduce visual information, the KL-divergence, and give the definitions to what singular models are. And hopefully, if we have time, we'll just introduce Bayesian statistics, but probably not. And throughout, we will hint at the role of geometry in learning. So throughout, please feel free to comment in the comment box or something to type out your comments or just interrupt me. Okay, with that, I think I'll just move immediately to the second board. Okay, all right. Okay, so I think I'll pick up from the supplementary session last time. So if you recall, we were talking about a coin flipping person on the other side of the door, and he gave us a bunch of observations, a bunch of coin flips, and our task is to estimate the probability of landing heads when he throws the coin again. Well, we see that statistical inference involves the following object. So we have what we call the true distribution, or sometimes known as the generating process. It generates a bunch of observations, which collectively we will call the data set. And then through some learning process, something called that we shall call p hat is produced, which is supposed to be an approximation to the truth, to the true distribution. And we saw that one way to have such a learning process is to first define a model, which is a probability. A model is a probability distribution, a family of probability distribution parameterized by a parameter living in some parameter space W, and together with the data set and the model, we can define something called the likelihood function, which is a function of the parameter. It tells us for each parameter, what is the likelihood of observing the data we observe. And here we have used the IID, which is identically and independently distributed sample. So meaning each sample comes, we are assuming come from the same distribution and they are independent, hence the factorization. So the learning process with this model would be something akin to finding the maximum likelihood estimate, which is just the R max. So maximum W, the parameter W that maximizes the likelihood function. In which case, the MLE approximation to solve this learning problem, to solve this statistical inference problem, will be just to set P hat, the approximation that we want, to be the model at the MLE. And setting the approximating distribution to be exactly a model at a point to choose a parameter is called, in general, a point estimation, because we are choosing a point in the parameter space, the best point of some sort according to some measure. And the measure in this case is just the likelihood function. Okay. Let's move to the next board. I'm hoping the orbs is following. Okay. Okay, we also see that, oops. This point estimation, MLE or otherwise, which we call the estimator, because it estimates its role is to estimate the parameters, is a random variable. Because it depends on the random training samples produced by the true distribution, which we call Dn. This thing is random, and W hat, the estimator, depends on it, hence it is itself random, and therefore it has a distribution, which is usually called the estimator distribution. So in the coin flip case, we saw that the estimator distribution was something like, I don't know why that line get in. Is actually a binomial distribution. And by the theorem that says that when the number of binomial trials becomes larger and larger, the binomial distribution actually gets approximated by the normal distribution very well. However, if you actually do the sampling and do these experiments a lot of times and for different true value, meaning, for example, if the coin is extremely biased versus if it is not very biased, let me draw that out. So in the completely fair coin case, you will be, you might perhaps generate, say, 50 observations, and the normal approximation is already a really good approximation, even near the tail end. However, if you use the same, if the coin were a very biased coin, for example, its true probability of landing head is 0.01, then your data set, if you only have 10 flips, most of it will probably be tails, in which case your binomial distribution will be very, very skewed. And the normal distribution, it will still be a fairly good approximation near the mean, near the peak. But then if you don't have enough sample, the normal distribution will have very, very low variance, and hence it will extend into like the impossible region, which means the normal approximation is a really bad estimate when n is not very large. You need, as you go in this direction, need larger sample size to get good normal approximation. So you need the sample size to be big enough that the normal distribution become that sharp. And even worse, near the endpoint here, for example, not for example, it's precisely the 0 and 1 endpoint. So if your coin is literally both heads or both tails, then there is no normal approximation possible. So those are the pathological points that shall concern us in singular learning theory. And we see that even when the true distribution is not pathological, like it is not at the pathological points, the pathological points kind of reach out to its neighborhood and influences how difficult and the distribution can be estimated by a normal approximation. So that's kind of a hint at pathological points, or as we will see later on, which we shall call singularity, influencing the learning behavior on things. Some comments on this special case of the coin flipping models, that this situation with the MLE being asymptotically normal. So this property of being able to be approximated by a normal distribution as the sample size get larger and larger is called asymptotic normality. This is not a coincidence. This is this actually holds. This property holds for MLE, so maximum likelihood estimator, of regular model, of something called regular models. But this is where we shall define something called the Fisher information matrix to see what regular models are. Okay, let's move to the next board. Is there any question at this stage? The OpCam is very skewed.
Just come back to your left a little bit, all right?
Come back to the left.
Yeah. Yeah.
Okay, that's too much, too far.
Yeah, stop.
Okay, that look good.
Maybe that's
okay, cool. Okay, cool. So even in just slightly more complicated situation, like slightly more complicated than the Bernoulli variable that we were dealing with in the coin toss case, we won't have the luxury of computing the estimator distribution, which turned out to be the binomial distribution in the coin toss case directly. Which means to find asymptotic approximation, to find the asymptotic distribution of the estimator, we need some other machinery. So this is where let us define the Fisher information matrix. The Fisher information matrix of a given model is the expression we denote I the function of the parameter, it's equal to, I'm going to write out the idea first, is equal to the covariance matrix, where the covariance is taken over as if the data is sampled from the model, sampled from the distribution at the model parameter prescribed by the input. And it's a covariance.
Sorry to interrupt. Could you just move closer to the orb? Just stand closer to it.
Closer. Okay, where's the orb? Got it.
Over here. Yeah. So if you just stand in front of it, people will be able to hear you best.
Okay, cool. Is this better?
Yeah, I think so.
Okay, cool, thanks. Okay, so it's a covariance of using the distribution at W of the following vector. So it's a vector of partial derivatives of the log likelihood. So let's complete the definition first before I give the intuition. So in component form, the expression, so this is a matrix, the ij component is given by the integral or the sum if you are dealing with discrete random variables. So that's the distribution at W. So in one dimension, just to give us some intuition about this thing, in one dimension, this reduced to a scalar function. So it's a 1-by-1 matrix, so it's a scalar function, which is equal to this expression. So this is saying, so assume that the data comes from the distribution there, and we ask, what is the variance? Because this is the diagonal component of covariance matrix, is the variance of what is the variance of this gradient, the gradient of the log likelihood. So recall that we use this expression to get MLE, the condition for, at least a necessary condition for a parameter to be the maximum likelihood is that this is 0, to be a local maxima is that this is 0. We use this to derive an expression for the MLE. But perhaps even more, even better for intuition would be if the log likelihood is nice, is sufficiently nice, then we actually have a better expression for this, which is equal to the negative of the second derivatives. So this is not the square of the derivative anymore. This is the second derivative of the log likelihood. So what is this expression? This expression is the expected value of the second derivative. So perhaps a better way of saying that this is, again, assuming that the data is coming from a true parameter, what is the expected curvature of the log likelihood? Let's move to the first board again, and I'll give a few examples of the efficient information. Okay, let's give the example using the model that we have been discussing throughout, which is the coin toss model. So recall that the probability of heads at the model parameterized by W is just given by W, where W is just thought of as the probability of the coin landing heads, and which forces the probability of landing tails to be 1 minus W. And that, if you go through the computation, you get the Fisher information matrix in this case is equal to this expression. If you plot the graph, so that's the W-axis, this is the Fisher information, which is a scalar function in this case. So there's an asymptote near the endpoint. It's quite flat there. So that's the function. Right. And notice that it is not defined. It's not defined at the endpoint. And also notice something quite important. So last week, we derived that the estimator converges in distribution to the normal distribution with mean equal to the true parameter. So that's the unbiased statement, that the MLE is an unbiased estimator of whatever the true value is. And the variance was computed last week using the variance of the binomial distribution, and it's equal to this expression. So that's the variance. And we notice that this expression is actually equal to 1 over n multiplied by the inverse of the Fisher information. So there's a kind of a name for the inverse of something being the variance, which is called the precision. So the Fisher information can be interpreted as a precision of the estimator, but to be more precise, it is the asymptotic precision. So this is actually not a coincidence. Again, because in regular model, MLE is asymptotically efficient. So this property is saying that as an estimator, to estimate W naught, actually, let me write this as, whoops, that's too much. Anyway, let me go to the next board and write this as a theorem. Okay. So theorem. So under some regularity condition, which is a little too complex to state in its full generality, but you should think of what are the various different assumptions that we made when we calculate our maximum likelihood estimate, as we did last week. For example, the likelihood function should at least be differentiable. Under some regularity condition, we have the following convergence So this is for any model. This is not the coin toss model anymore. So this is just any maximum likelihood estimate for some model of some truth, which we also assume realizability, meaning the true distribution, the generating process, is actually part of the family of model. Under those conditions, this random variable converges in distribution to the normal distribution with mean 0 and the picture information matrix in this case as the precision matrix, which means the inverse of the matrix, so that's the inverse, is the covariance of the normal distribution. This is multivariate normal. So even under those even if some of the regularity conditions are satisfied, we still need something for this statement to even make sense, which is that the inverse exists. We need this to be true. And this is perhaps the more important condition in what we meant by a regular model. So definition, a model is regular if it satisfies two conditions. One is the non-degeneracy condition that Dan was alluding to last week. And it is phrased as it is the identifiability of the model. If it is identifiable, this means that if you have two different model parameters, you should have different model. Different parameters parameterize different models. So, not equal. So not equal as distribution of X. So it could be equal outside of the zero set, for example. Sorry, I meant it's not equal as distribution. So the condition is just for a set of outside of the set of measure 0 is fine. But if it's assumed continuous, then this is just not equal as function of X. The second condition is the condition that we were just talking about, which is that the Fisher information matrix of this model is everywhere invertible. This is actually not how Watanabe stated in singular learning theory, but this is equivalent to the condition that the Fisher information matrix is everywhere positive definite. So if you recall that the matrix itself is a covariance matrix, which means that it has real entries and it is symmetric. And because of that, we have real eigenvalues. It is diagonalizable. So, and also you can prove that because it's a covariance matrix, it is definitely positive semi-definite, which means that all its eigenvalues are greater than or equal to 0. It's non-negative. But we do need, for a model to be regular, you need it to be definite, meaning that all the eigenvalues are strictly greater than 0, which is for positive in the family of positive semi-definite matrix, that those are precisely the invertible matrices. And here we can define a model. We can define what singular models are. A model is called strictly singular if it is not regular. So if it violates one of those two conditions. And singular models is just an umbrella term that encompasses both the regular model and strictly singular models. Any question at this stage? Let's move to a new board. Okay, let's give an example of a singular model. We saw an example last time where we could have a more complex model of the person tossing coins on the other side of the door, even though we observe exactly the same sequence of heads and tails. We could assume that he is doing something nefarious and he's actually choosing one of two coins from a box at random, one of which is a spare coin and one of which is a biased coin. And our model in that case become a two-parameter models. So we have two parameters where S is the probability of choosing the fair coin, which means that the probability of landing heads is, well, first the probability of choosing the fair coin and then multiplied by a half, which is the probability of landing heads in a fair coin, plus the probability of choosing the other coin, which have probability of landing heads measured by W. And on the other hand, the probability of landing tails is just 1 minus the expression, or you can just work out the logic again, is this expression. And note that this is not identifiable, meaning it has some degeneracy. In particular, if the supposedly biased coin in the box it actually has probability of landing heads of W equal to half, meaning it is itself a fair coin, then this model collapsed down to just a fair coin model. This is just saying that if W is a half, then the probability of landing heads is the same as the probability of landing tails, which is equal to a half for every value of the parameter S in its own parameter space. So this is the degenerate condition. So we have two parameters. One is W, one is S. This line of W equal to half all parameterize the same model. And I spent some time computing the Fisher information matrix in this case. So if we call this expression A and this expression B, because I don't want to write them out a lot, this Fisher information matrix is actually given by W minus half square 1 over A. And because it's symmetric, I won't write this out. It's just the same as the off-diagonal component. So that's the Fisher information matrix. And you observe that on that line of degeneracy, when W is equal to half, so that term becomes 0. And when W equal to half, the expression A and B are actually the same thing. So this is 0. So the only non-zero term is this term. If anyone have time, please do check my calculation and see that this is correct, because so this example is taken from Xiaowei's Lin thesis. And he actually got a different answer than I did. So I haven't checked mine. He got A here, but someone please do check. Let's move to the second part. So this is an example of a degenerate Fisher information matrix at some parameter. Moving to the next board. Any question about this so far? I think I moved too far again. Whoops. Come back. Okay, stop. Stop. Okay. That's fine, I guess. If there's no question, this is perhaps a good time to introduce another very important quantity, which I shall explain what its connection to the Fisher information is, which is called the Kullback-Leibler divergence. So AKA the KL divergence. So it's between two distributions, P and Q, but it's not a symmetric function between the two distributions. So we usually phrase it as the KL divergence of a distribution P of X from another distribution Q of X, denoted as such. Is equal to the expected, and expectation is taken over Q, the first distribution, of the following expression. If anyone is familiar with information theory, recall that the log of a probability of an event is sometimes known as the surprise of the event. For example, if I tell you that the sun will rise in the east tomorrow morning, that is not a very surprising event, and therefore the information content from someone telling you that the sun has indeed risen in the east is a very low value piece of observation. So the information is low in that case, and the log of that is low in that case. The surprise is very low. So this is kind of the difference in surprise with observation taken from Q. So this is like saying if you have if the true event generator is Q, but your belief is that you are modeling it with P, what is your excess surprise? That's kind of just the intuition of it, and it's equal to the expression of, if you write it out, is equal to this expression. And some important properties is that it is always positive, non-negative, and it is zero if and only if Q is equal to P, well, almost everywhere. Well, it means that they are the same as distributions. I think throughout we will assume that our distributions are at least continuous, which means this is just equality of function of X. Any question about this? Okay, if not, well, I'll mention its connection to the Fisher information matrix. So recall that the Fisher information matrix, let me just write it here again. If W0 is the true parameter, and again, assuming that the log likelihood function is nice, is sufficiently nice, then this reduced to the second derivative. I'm going to use the one variable case for now. So it is that, and sorry, those are W0. And if the true distribution is actually realizable and is equal to the model at W0, then this is Q of X. And the difference between if and assuming also that you can swap expectation and derivative, that's apology about the various assumption, but you can prove this in some nice situation with dominated convergence. This is not too strong a condition. So if you can swap that, then you can see that this expression is actually equal to the second derivative of the above expression of this expression at the true parameter. So this is the relationship between Fisher information and the KL-divergence. So this is saying that Fisher information is equal to the curvature of whoops, I forgot to define another thing, which means that some of the things I'm saying here is not doesn't really make sense. Okay, let me define it here. Sorry, a small definition that is related to the KL-divergence here. So in the setting of having a model P of XW, we define a function called K of W, which is what I'm trying to talk about below here, to be equal to the KL-divergence between the true distribution and the model at W. Okay, so let me complete my sentence below before I draw some pictures. The Fisher information is equal to the curvature of this function and this rather important function at the true parameters. Okay, let's move back to the first board to see some pictures and finally see some geometry, hints of geometry. So if we think of our parameter space W as some blob, well, it's a parameter space, so embedded in some d-dimensional Euclidean space. Each parameter, W1, so sort of represents a model, a guess of what the true distribution is. The realizability assumption just says that there is a parameter called W0 somewhere whose whose model that it represents is equal to the true distribution. And the function, the Kubert-Leibler divergence, the KL-divergence between two distributions can be made into some sort of quote-unquote distance. So distance between two distributions. So it can be descended into a distance of the parameters. However, the KL-divergence is actually not a metric in the sense of metric space. It is not symmetric, as we said. So distance from W1 to W2 is not the same as W2 to W1, and it doesn't satisfy the triangle inequality. However, there is some sense in which you can make it into an actual distance by making it a Hessian metric, which is a Riemannian metric. But that's only if the Hessian, which as we discussed before, is equal to the Fisher information, is non-degenerate. So that only occurs in regular models. So the reference here should be sort of information geometry, which assume regularity and therefore can define a metric. And then the actual distance between the parameters is given by the length of the shortest path using that Riemannian metric. But for our purpose, we would just think of it as quote-unquote distance. And the function k is just the quote-unquote distance between the true parameters and other parameter. Okay. I should also introduce, while we are at it, for a given model, that is modeling observation so that is generated from a true distribution Q of X. We define the empirical log likelihood, well, not quite log likelihood, because we have that already, is the log likelihood ratio, which is the ratio between, so this is the likelihood ratio between Q, the truth, and the model at W, and we're taking the average of that over the data set. So this is called the log likelihood, empirical log likelihood ratio. It's a random variable because it depends, again, on the data set. And if you take expectation over the data set, so expectation over the Q, well, you recover the KL-divergence, the K function, which sometimes is called the expected log likelihood ratio due to this reason. So by the law of large number, this expression on the right converges in distribution to the right-hand expression, which means that this expression on the right is approximated really well by the expression on the left when n is really large. And just to point out that Kn is equal to, if you write this out in terms of two sums, is equal to well, negative 1 on n. Well, the second term is just the average log loss. The log likelihood is in here and it's negative, and take an average of this is the average log loss. And the first expression is the empirical estimate to the entropy of the true distribution. Okay, let me draw another picture here. So it could occur that we have this realizability condition, but the non-identifiability possibility can be represented pictorially as having an entire well, it's a variety of things, of parameters that represent exactly Q. So this set, which we will denote as capital W0, is equal to the set of W such that the model at W all equal to the true distribution, which, because of the properties of KL-divergence, this is equal to the zero set of K. And this set of parameters could have something like that occurring, which would be a singularity, which this is an example of a singularity. So some other example of singularity for plane curves, for curve that I can draw on the blackboard here would be something like the Cups singularity, and this is sort of a crossing. Or you could have something doing some tangential business. So, and what I would say for now, and will be made rigorous and make clear, is that the geometry near singularity, let me be a bit hyperbolic and say that it determines learning behavior. Okay, so that's the hint of the role of geometry in statistical learning that I'm going to give this lecture. I realize that there is a lot of technical definition to get through, and this is this is all we can get up to for this lecture, and I think we will see the consequences of this and maybe set up Bayesian statistics, the Bayesian point of view, instead of the maximum likelihood estimator. There is tons of other different ways you can construct the approximating distribution p hat from the data set and from models. We'll see the effect of singularity of this set in the future. So from now on, when we talk about singularity of a model, we meant singularity that occurs at the zero set of the KL-divergence of the model. We mean this W0 set. So any points, any non-smooth points in this set. Any question? That's all I am going to say for this talk. Is there any question?
Yeah, I have a, maybe not a question, but maybe a broad comment, right? So information geometry doesn't really appear all that much in Watanabe's work, right? Is there a place for this stuff, like with the the Riemannian metric on that manifold, or is it kind of a little bit separate from the singularity stuff that he's talking about?
So I was just discussing this with Dan, and I actually noticed from like the fifth read through of the first chapter that in the preface of Watanabe book, the author actually thanked Professor Shinichi Amari, which wrote the definitive textbook on information geometry in his book. So they definitely know each other, and I think at the moment the concern of these two different fields, even though they share sort of the basic setup, is quite different. Whereas in SLT we focus on where the visual information metric goes wrong, and in information geometry they focus on
Right.
the effects of curvature and everything like that. The upshot is that I don't actually know much about information geometry, and the language seems to be the same, but I don't know of any direct connection to information geometry beyond the shared definitions.
Okay, cool.
It could be a very important thing to explore, though. Like, is there any implication of singularity and resolution of singularity as developed in SLT to information geometry? I couldn't comment on that. Maybe.
Yeah, my very naive thought would be that if there's more structure on that space, like, you know, there's like a degenerate metric, right? You know, can we use it? Maybe not, because it kind of flies off, right? That's exactly where those points where the metric is degenerate or singular or whatever. And maybe tools from Riemannian geometry is just not equipped to handle it. And you have to resolve it, right?
Yeah.
Okay. Yeah, that makes sense.
I think Dan mentioned something about if it is minimally singular. I forgot in what sense, like when it is just degenerate in a few directions and still maybe, okay, in minimally singular, I think reference Dan's deep learning in singular paper appendix. I wouldn't try to recall the definition here. Then information geometry actually have something to say about things, then it sort of still applies, still fixable. But I think you made a really good point, which is like, what if we could do information geometry on the resolved space? Maybe. I don't really know the implication there.
May be able to do it. You're going to have trouble extending that metric over the exceptional locus, though.
Yeah.
Yeah. You know, there's certainly not a unique way of doing it, right? Even if you can. Anyway, yeah, thanks.
Yeah, no worries. Any other question? I think for some of the as singular learning theory people here, this is very much a revision. I'm sorry if that's a bit boring.
Is there a supplementary session today?
Yes.
Yeah, I think there is. Liam?
There sure is.
Sorry, Liam, I didn't actually set up. Yeah,
no,
sorry, I didn't
that's
actually got to Bayesian statistics, and you might need to do the heavyweight. If people want to, I can start writing out some Bayesian statistics stuff while we're on the tea break. Actually, I think I will do that while people go off. I just write it on the board or something.
Cool.
Yeah,
Sounds good.
no
I got to
worries.
drop. I'll be back in half an hour.
Okay, cool.
Cheers. Bye-bye.
So I believe this is tea break time. Okay. Okay, so I guess stop the recording, and I will just start writing some Bayesian statistics stuff while you are welcome to ask me any other question about singular learning theory or ask Liam about it.
Thanks for the talk, Edmund. It's
No
very
worries.
good.
Thank you. I guess I can disconnect from the OCam. Thanks, Ethan. If anyone wants to stick around, I'm just going to write out some Bayesian statistics stuff.